Oh no.
I
Yeah.
I don't have a calculator, like the ones that we can use. I know, like, is there any chance I can use my phone? Or, like,
Sure, you can use your phone.
thank you.
Yeah. Oh yeah. Yeah, if you need a quiz, they're up here. Apparently I didn't prepare a lecture for today, so all right. Welcome to what's this class again? 2K2, yeah. To 2K2. Yeah, so this is I think everyone's favorite class.
Yes.
Has a very good reputation. All right, so just for those of you that are struggling, there's kind of two pieces of good news, which are that this is like what's considered the hardest class in the major. So if you're not that lost, then you're gonna be okay for the rest of your. And then the second piece of good news is that we've officially finished talking about transistors. So there won't be any more transistors in this class. Till the final, yeah. There's gonna be a couple questions there. So test 2 and 3 and 4, or test 2 and 3, and the final is like a test 4 plus some extra questions too. So it's like heavy on the last material, and then 100 points are the last material and 100 points are cumulative, basically. Are all on completely unrelated topics to amplification. So just a reminder about our class breakdown. So far we've done this, we've done this, and then next class we're gonna basically do this, which students don't have a lot of problems with op amps. And then after that, no more amplification, and then we're just gonna go back to good old resistor, capacitor, inductor circuits. But before you were doing these phasor domain type solutions, now we're actually gonna solve them in the time domain, so you're gonna actually get the full response to the circuits. And that's gonna be kind of test 2. If you've taken out differential equations, we're gonna be doing a lot of that. How many of you are taking currently differential equations? Oh wow, okay.
2K1 last semester was very at the same time.
Okay. Well, it's a co-requisite. Okay, so that makes, okay, anyway. I'm probably gonna go over this a little bit faster than I was planning to so that I can buy more time for differential equations. Okay. We do very simple stuff with differential equations, but it is harder for students that haven't taken the class already. In general, that's the other third part of the good news, that when people say this class is bad, they really mean this is bad. And so we're talking about 1/3 of the class. And so you have to realize that just because you're not doing well right now doesn't mean that you won't do well in the future. But do kind of, I always tell students this because I know basically students struggle with this. If you can make a 50 on the first exam, just basically don't make a catastrophic. If you don't get out of here with, if you get out of here in a bad position but not a catastrophic position, then you'll be good. That's kind of what I tell students, that because the grade is only going to go up, basically. That's kind of what I typically see. And so what you don't want to do is get a 25 here, or, like really, really tank. That's kind of what you should be thinking about. And of course, what that means is that you only need to get half the questions right in an exam. So if you don't know one question, there's no reason to panic. Anyway, yeah, that's kind of my advice. Today we'll see how well you actually do know or don't know this stuff based on the quiz. All right, so let's go over a review of so far everything we've done throughout this class. So we introduced the MOS transistor, and we said it had 3 regions of operation: cutoff, triode, and saturation. And then we said that for each of these regions, there would be 3 different IV relations. So if you're a cutoff, there's no current flowing through these circuits. If you're a triode, then the current approximately behaves linearly as a function of VDS. So its factor tends to be a lot smaller than the second one. Then finally, if you're at saturation, the current is approximately flat. And in fact, we said that in this class, we would always assume that as a function of VDS, when we do DC analysis, we wouldn't actually consider that second term, so it is completely flat. And the second term was due to channel length modulation, the non-flatness. Then we said we were going to distinguish between 4 types of transistors. They're the N types and the P types. The N types move negative charges, so the current flows from the drain to the source. And then the P types move positive charges, so the current flows from the source to the drain. Additionally, so basically you're moving positive charge, so it's always the source to the drain is kind of the current direction, whereas since you're moving negative charges, it looks like a current going in the opposite direction from the source to the drain. Yeah, so what we said is that these 2 types of transistors would be actually mirror images of one another. So you could either say the same inequalities follow for both sets of transistors, but the polarities of the inequalities are reversed. Or you could say that the inequalities stay the same, but wherever there's a BGS, gets replaced with VSG, and wherever there's a VDS, it gets replaced with VSD. And then here you would use kind of the absolute value of V threshold. Typically we don't do that. We just say the inequalities are reversed between one and the other, but do realize that in PMOS, unless you're in normally on mode, your VGS, VDS will always be negative when your transistor is on, whereas in NMOS, it'll always be positive. Additionally, we said that there is these 2 other types of PMOS and NMOS, which effectively were normally on, and they were denoted by this bold line. And all that meant was that the value of V threshold was less than 0 for the NMOS and greater than 0 for the PMOS. But really what it means is that you don't need a voltage between the gate and the source to generate your channel, and your thing will be normally on. And those are called depletion mode. Questions about these things all the things that I just said? No questions? Okay. Okay, so we went over that. We went over solving DC circuits, and then we basically introduced our small signal model. And what we said was that at DC, all capacitors behave as open, and so we could actually separate out the analysis of a circuit that looks like this, where there is DC sources and AC sources, by first solving the DC circuit, where you treat all capacitors as open and you deactivate all AC sources. And then once we solve this circuit, we could derive a small signal model. And then from the small signal model, we could actually come up with our small signal equivalent circuit, and then we could solve that to come up with the time variation of the voltage. So in particular, we kind of said all the quantities would be kind of the ID plus little ID, VDS would be plus little VDS, and the little ones the big ones represent the solution for DC, the big ones the solution for the small signal model, which you derive doing your small signal analysis. In particular, we never actually, when we looked at our circuits from this perspective, we never actually kind of did these sums explicitly. The reason is because we're looking at these transistors as amplifiers, and what we want to do is amplify a time varying signal. So we're not really interested on what happens to the DC signal. We're actually interested to what happens to that time varying part. Why is that? Well, like if I look at this microphone, when I turn it on, there's kind of a DC bias on the signal, but you don't really want to hear that DC signal. What you want to hear is my voice. Maybe you don't want to hear me, but anyway, that's presumptuous, right? I don't know. But anyway, the point is that you don't really care about listening to what Duracell here has to say, which is just 5 volt or whatever. I don't know. You care about is that time varying signal that's being picked up by the microphone. So what we're really solving is for that time, just the time varying part of the signal. Okay. So anyways, we derived a small signal model, and then we were able to get a circuit like this. Are there questions about this?
So I have a question.
Yeah.
So you know how common source right now is called common source because the capacitor is shorted, the source is shorted, right?
No, well, it's common source because the source is the one that's connected to ground once you derive that small signal.
If we remove the MOS and put PMOS, would that still be common source, or would that switch to common drain?
That would still be a common source. No, that would be a common drain.
So would that follow the equations for common drain, or would we have to derive another equations?
You would have to derive a whole new set of equations
Okay.
because the circuit is fundamentally different. If that makes any sense.
Yeah.
So your small signal model is going to look different. That's just not going to happen in an exam, just FYI. So
Okay.
you can have all the nightmares you want, but but that's just not going to. What's going to likely happen is that you're going to get a common source that's simplified version of this circuit that you haven't seen before. But it's going to be simpler, not harder, if that makes any sense. Here, I'll tell you this much. We've never asked a question in an exam where there's a PMOS on an amplifier circuit. And I've taught this class 7 times now.
That's huge. That's huge.
There might be a PMOS on the H circuit, but not on the. So we don't do PMOSs for small signal analysis. Go ahead. There's one in the homework, but not in the exam.
So when you ask for a small signal model, do you want us to make something like that with like a voltage source that has like AVI, VI, or the one that has the current source, GMVGS, or it was like?
Are you asking about the quiz?
No, not. Like,
The small signal model would be the one where you just short all capacitors and you replace this with your small signal model. This is your equivalent amplifier circuit.
Okay, so that's just a different.
Yeah. But so you use your small signal model to derive these three things. That's why we want to get that small signal model. But so in the quiz question 2, B, do not write this. Draw the one that we're gonna actually do in a few slides. Okay, well, that concludes our review. Let's start the quiz. Just kidding. Go ahead. Questions? No? Okay. All right, let's go over some sample questions until we run out of time. Okay, can you identify the different regions of operation? What kind of transistors are these? All right, so how many of you don't know what region of operation this is? So it's either cutoff, saturation, or triode, or VDS sat. If you had to guess, what would you guess?
I would say triode.
Yeah. So it's triode. And then triode, because you have a current that varies linearly. Then you have as a function of VDS. And then you have here that this is cutoff. And then we typically call this point VDS sat, because it's kind of the point where you transition from triode to saturation. So I think we asked this in the final last semester. Most students got this though. Okay, so that's kind of the 4 regions of operation. Now, this is VDS as a function of ID. You have to also remember that when you look at that this circuit, there's kind of a load line. And so we typically have, if we look at V, is it DS or GS? GS goes to infinity. VGS, and then we look at VDS. We kind of have a plot where here, when there's no ID flowing through this, so when we're at cutoff, if this is VDD and this is VSS, we're gonna have that this is VDD plus VSS. And then here we have V threshold. This is for an NMOS. And then as we increase VGS, the current will initially decrease linearly, and then eventually it will kind of asymptote to 0. Sorry, VDS will asymptote to 0, which is the case where ID approaches. So ID is going to approach VDD minus VSS over RD and R plus RS. So this is RD here. This is RS. Now, what region of operation is this? Huh? Yep. Yeah, this is saturation. And it's because the current is changing as a function of VGS quite aggressively. How about here? So how much current is flowing through this circuit when we're here? So if all the voltage drops, so remember that VDS is the voltage drop across the transistor. So there's 0 current flowing through there, which means that this is cut off. And then finally, this is, triode. So just remember that, there's all these VGS lines, and then you have your load line, and then where your load line crosses those VGSs is where you're operating. And so if you keep increasing VGS, eventually you're just going to be in triode. And then in some middle portion, you're going to be in saturation. And then if VGS is 0, then you're going to be at cutoff. So just kind of, you have to know these two graphs, not for today, but I hope that's not new. No. What are we doing here? All right, okay. It's gonna give me feedback on my teaching now. All right, okay, so let's forget about everything I just said. And what kind of transistor is this plot? Does anybody know? Yeah, it's an NMOS enhancement, and the reason it's NMOS is because as you increase VDS, you get more current, and then when you have positive VGS, it's on. And then in particular, which are the depletion types? Is this one depletion? How about this one? And this one? Exactly. So because you get a non-zero current when VGS is 0, these are the depletion ones. Okay, so you know everything about these IVs. Okay, so I don't think this is going to show up in a test, but it's shown up in the past. So we're going to go over it. Oh, okay. So if I increase VGS and the current increases, what kind of transistor is this? Yeah, so if I increase VGS and I see an increase in current, I know for a fact that this has to be an NMOS, because remember that I have that ID equals GS minus V threshold squared K over 2. So in the case of PMOS, this would be a negative quantity, so in magnitude it would become smaller, so I would get less current. So it is an NMOS because of that. Now, if this for this same type of so now we know it's an NMOS, but now for this same kind of transistor, now I plug in a negative VGS and I still get a current. What does that mean? Is it enhancement or depletion? Yeah, so I basically go to my voltage source and I make VGS negative, and I still get a current. It's the same transistor, so it's an NMOS, and then I just put it. Yeah, so it's a depletion mode.
But isn't depletion at 0 is also negative?
Yeah, because the value of V threshold is negative. So as long as you're less negative than V threshold, then you're still going to get current. So just why would this be relevant? Well, when you look at your transistor, you're not going to see this little symbol with. What you're actually going to have is this little like black piece of plastic, and it's got to have 3 terminals. And you might not know what type it is, so you can run these experiments and figure out what it is.
Sorry, summer I just
Yeah.
took out a car in the middle of the highway.
Okay. Yeah, it's pandemic time, I know. Okay, so let's look at the second one. I don't decrease, I decrease, so let's not get violent here. Okay, so you decrease VGS and the current increases. So now this is a new transistor, and what you see is that when you decrease VGS, the current increases. What does that mean? Yeah, it's PMOS. Okay, cool. Yeah, so you kind of get the gist of how you could also ask these questions verbally, and you don't necessarily have to ask them graphically. Assume -1 volt threshold. Okay, so if I told you that for this NMOS transistor here in enhancement mode, B threshold was -1, would you be able to tell me what K is? Okay, so what is the value of ID when BGS is 2 of ID in saturation? For this transistor here. No, the value of ID when BGS is in saturation, when BGS is 2 in saturation.
0.5.
Yeah. So basically, you look at the blue line, and when you're in saturation, you're going to have that ID as 0.5. Okay, but since we're in saturation, that's just really K over 2 VGS minus V threshold, and I kind of messed up here because I should have actually asked you about the PMOS, so this should be a PMOS transistor. And for this PMOS transistor, we actually have 5, not 2, so 5. Wait, that's the depletion. So no, 0.5. It's still 0.5, yeah. Okay, so we have 0.5. So now since you know VGS is 2, you know V threshold is, or -2, V threshold is 1, and you know this is 0.5, K over 2, you can actually figure out what K is. So in this case, 1 equals, this should be squared. 1 equals K. Is that clear to everyone? So since I gave you V threshold from this, I told you as enhancement from the sign, you should have known it was a PMOS. And then these plots give you, at least for some value of VGS, what the saturation current is. And so you can use that to extract the 0.5. And then from that 0.5, the only thing you're missing is K. Yeah?
That's in milliamps per volt squared, right?
Yeah, because I wrote this in milliamps. So 1 milliamp, and then this is in volts, so per volt squared. Okay, cool. So that's basically almost everything I can ask you about by showing you IV relationships. I don't know, I'll have to come up with something new, but I don't know what else I could ask. So we're gonna look at some interesting circuits that I haven't seen for a while, but let's look through them. So this particular circuit, we have that I equals 0.1 milliamps, VGS equals -1, lambda equals 0, and V threshold equals 0.5. So they told us all these things. What is the region of operation of this circuit? Can anyone tell me? So BG and VD, how are they related? Okay, so VG equals VD. This means that VGS equals VDS. And then I'm gonna subtract V threshold, so VGS plus 0.5. How is that related to VDS? Yeah. And this is a PMOS transistor, so what does that tell us about the region of operation? Remember, so for PMOS, all the inequalities are reversed. Yeah, so this circuit is in saturation. What that also means is that ID equals K over 2 VGS minus V threshold squared. Now, in this case, what is ID? Yes, it's 0.1 because no current can flow through here. So whatever current flows through here has to flow through here. So 0.1 has to flow through here, but well, that's just ID. And so that means that ID also flows through here, which is 0.1. Okay, so we know ID. So we have Cool. So basically we know everything about the circuit at this point. Cool. What is V4? Okay, so that is the question. What is V4? Okay, yeah. So at this point, we don't know what VG is, and they're asking us what V4 is, which is what VD is, and so we can actually rewrite this by putting 0.1 equals, they also gave us K, did they give us K? Assume I, VGS, V threshold, K. Wait, you should have to know, okay, don't you? Oh, they gave us VGS. Okay, sorry. So you don't need to know K because you know VGS. Okay, since you know VGS, and we know that VD equals VDS, and what is VS? Yeah, so we have that -1 plus VS, which is 1.25 equals VD. So that's gonna give us that VD equals 0.25. I think that's pretty much all you can do with the circuit at this point. I mean, does this make sense to everyone? Yeah, so I got ahead of myself. All right, so now let's make this question more interesting. So now I actually stick a resistor here, RD, in between VD and VG. Now, how much current has to be flowing through this circuit? What? Yeah, so still 0.1 because this thing's still open, so basically 0.1, which means that VD will be equal to what? So VD will be equal to VG plus RD times 0.1. And so that means that VDS is equal to VGS plus RD times 0.1. And for saturation, what do we need? We need that VDS is what? 0.1. Well, that has to be less than VGS minus V threshold, which in this case is negative 0.5. So what does that mean? In order to satisfy saturation, what does the RD have to be?
Bigger than that?
What?
Is it bigger than or less than?
Well, this is a PMOS, so it's less than. So this means that RD, so 0.1 RD has to be less than, the VGS is cancel, and you're left with 0.5. And this is in milliamps, and this is, and this is in volts. Yeah, so we have that RD has to be less than 5,000 kilo or 5,000 ohms. Cool. So that could be a circuit we could give you on an exam, basically. I haven't seen these circuits in like 4 years, just FYI. Okay, so now we're gonna actually look at a small or a DC equivalent circuit. So in this particular case, what is the DC equivalent circuit? So what do we have to do here to make this into a DC equivalent circuit? How much time do we have? So what do we, when we're trying to find the DC circuit and we're doing small signal analysis, what do we do to capacitors? Open them. And then what do we do to DC sources? If we're trying to do DC analysis, we keep them, and then to the AC sources. Yeah, so, okay, so they're gone. So we deactivated it. And so our equivalent circuit for DC will actually look something like RD, R2, then it's going to here, this is grounded, and then here, and then 500 kilo, and then grounded. Cool, so that's basically it. And then this is 10 volts. Okay, so now this is the equivalent circuit with the VSig removed. So here's asking us a variety of questions that will actually lead to the solution. So the first question is, what is VG? That's an easy question. It's the voltage at the gate.
It's VD plus R2, I R2.
Yeah, so you can say that it's actually equal to, VG is equal to negative IR1 times 500K. Or you could say basically that it's VD minus, sorry, this should be a plus here, minus 2 mega ohms times, what is it, IR2. Okay, so how are IR1 and IR2 related? Yeah, they're the same because whatever current flows through here, there's no current flowing into the gate, and so whatever current flows through here flows through there, so this is actually equal. Okay, so one thing that we ignored when we derived these equations is that we told you here that VGS minus V threshold is 0.2, and then we were told also that V threshold is 0.6, So we have VG minus VS minus 0.6 has to be equal to 0. But what does that tell us about, what does this tell us about VS? That it's 0, and so that means that VG is 0.6. So it's also equal to 0.6. Okay, so that allows us to know what IR1 and IR2 are by using the equation we actually just derived, right? So we have that IR1 is actually equal to 0.6 over 500 kilo, and I think this is 1.6 microamps, if I'm not mistaken. I might be wrong here. Let me just go to the next slide. Yeah, 1.6 microamps. And why do I have 0.8?
Because it's 0.2 plus.
Oh, there's a 0.2 here. Okay, so this should be 0.8. I just don't know how to do math. Okay, cool. Okay, now that we know this, how can we figure out what, and we know that this is also equal to IR2, how can we use our other equations to figure out what VD is? So we know that this is 0.8. I mean, the equation's right in front of us, right? So we have that we could use this equation, which we already have, because we know IR2 and we know VG. Or we could use the equation for RD, but we don't know what RD is, do we? Yeah, we don't know what RD is. Okay, so at this point, we can say that VD minus 2 mega ohm times 1.6 microamp has to be equal to 0.8. The micro and the mega cancel, so you're left with 3.2 plus 0.8, which gives you 4. So that gives you that VD equals 4. Okay, so now we know what VD is equal to. And so how much current, so now that we know that this is 4 volts, what is IRD? Yeah, so IRD is just gonna be 10 minus 4 over RD equals IRD, but that's also equal to ID plus IR2. So we have that that's equal to ID plus IR2, which is 1.6 microamps. And then if we assume saturation, we can figure out what ID is, and then we can figure out what the RD needs to be. Okay, so we got that. Yeah, so okay, so we find that this is the value of our RD, and now we find that this is 1 milliamp. So do realize that these circuits are much harder than anything you'll have to solve in an exam. I'm just kind of going through the mechanics of it. At this point, okay, so we got our ID. How do we find GM? What is the value of GM? And RO for a small signal model. Yeah, so we just take this thing, so we get that GM is equal to the square root of 2K ID, which is just 2 times, K, what is K? 5, oh God, times 0.1. So we get that that's actually equal to 1. and it's in millisiemens, so, or milliohms, so you have to realize it's 0.001 if you don't do things in milliamps. How do we get RO? Oh, well, we were told that lambda is 0, so what does that mean about RO? Yeah, so RO is infinite. Cool, so 1 millisiemen or 1 milliamp per volt, and infinite. Okay. Yeah, so let's just draw the small signal model. We're not going to actually solve it, but let's just go for it. So how do we get the small signal model? We first have to do what to the sources?
Ground source.
Yeah. Okay, so, and then we basically draw our small signal model. The source is at the ground, so, and then we're gonna put the gate at our source end, and then the drain, and then remember that the GM, BGS. Okay, so then we go terminal by terminal. So the source just has one connection, which is ground. The gate has a connection between the gate, R1, and then V sig. So we're gonna have basically R1, and then V sig, and then that's ground. And then it's got this R2 between the, well, yeah, let's do it here first. So here's the drain, which is connected to RD and then ground. And then it's got R2, which is connected between the drain and the gate. So this is our equivalent circuit model for this particular circuit. Was that clear to everyone? And so this is the value of VGS. And yeah, so that's basically it. Okay, in the interest of time, I'm not gonna solve this one. I also remember now, yeah, anyway. So I'm always asked to give people more and more examples. But the thing is that, like, you need to know 3 circuits: common source, common drain, and common gate. So I never succumb. But then I get complaints, and then I just remember why I usually don't succumb. It's because you're just gonna get more confused. You need to focus on those 3. Like, anyway, but this circuit actually is one that I came up with. You're gonna build it in your lab, and I go over it every semester multiple times. What?
I watch on YouTube the answers too.
Oh, you watch the YouTube for this?
Answers too.
Yeah, the answers too. Anyways, I say this every semester multiple times, and then in the exam, 15 to 20% of the students get it right. So you're in that 15%. There's a review, I verbatim drew the circuit, and then the next day, like, we have a test review, verbatim drew the circuit, make a video, post it on YouTube, 500 views. The exam comes back, 20% of the students get it right. It's like I gave you the question. Like, what do you want me to do? All right, so for this kind of circuit, remember this is a current mirror, and in particular, we're gonna assume always when we look at these circuits is that they are in saturation. So in particular, because we connect the drain to the gate, in this particular case, what that means is that kind of VG equals VD, which means that VGS equals VDS. And then when we subtract V threshold from this one, so that means that VGS minus 1 will be greater than VDS. And since this is an NMOS, that means saturation. So in the previous example, since it was a PMOS, the orientation was reversed. Okay, so since we are in saturation, what that means is that our current for this particular circuit, ID, is governed by K over 2 VGS minus V threshold squared. Additionally, we know that VG equals VD, so we have that VS is 0, so this is actually ID equals K, which is 2, so I'm just going to plug in 2 over 2. And then we have VG, which is just actually equal to VD, so which is actually 5 minus 3K ID. So 5 here, and then when you fall to here, you lose 3K ID. So 5 minus 3K ID. And then VS is 0, so minus 0, minus V threshold, which is 1, squared. At this point, what this tells us is that we can just complete the square and come up with what the value for ID is. And so we're going to get that ID equals 4 minus 3 ID. And I'm dropping the K because I'm solving everything in milliamps. You could solve it in amps and then keep the 1000, it doesn't really matter. Then there's a squared here. For the sake of time, I'm just gonna guess that it's 1. So if I plug in 1 for ID here, I'm gonna get 1 squared, which is equal to 1, so that satisfies the equation. Additionally, if 1 amp flows through this thing, then this is 2 volts, which is greater than VD than V threshold, so we will be in saturation. So that turns out to be the answer. So I solve this equation, and I'm going to get that ID equals 1 milliamp. Cool. So now I know that 1 milliamp flows through this circuit. What is the amount of current flowing through this circuit here?
The same.
Yeah, so it should also be 1 milliamp. And what is the amount of current flowing through this circuit, assuming saturation? Yes, 1 milliamp. So remember, since these 3 transistors are identical, and they all 3 have the same value of VG, so VG2 and VG3 are the same, and VS2 and VS1 are the same. If we assume that they're all in saturation, they should all have the same current. Because their VGS is the same, so that means they have the same current. So that means that IX has to be, according to KCL, equal to the sum of these 2 currents, which is 2 milliamps. Is that clear to everyone? Now, what would be the voltage at this node here?
2 times 4.5.
Yeah, it's 4 volts basically. So 5 volts minus 0.5 times 2, which is still greater than VG. So you are indeed in saturation. So it is the correct answer. At some point, if I put too many of these things in series, it will break down. But yeah, that hasn't happened yet. So in principle, what I could actually do is I could put a fourth transistor here, and then connect it here. How much current, and then this M4 will also be identical. How much current will flow through here?
1 milliamp.
Yeah, 1 milliamp. So then how much current would be flowing through IX? 3 milliamps. So I can keep adding these, and then I would get more and more. Of course, I have to stay in saturation, so this VD has to be greater than, in this case, well, VG was, what did we say VG was? well, VG was equal to 5 minus 1 to 4. VG is equal to 4. So our VD has to stay under 4, basically. No, wait, 4, no. 1 times 3, 2. So 1 times 3 is 3, 5 minus 3 gives you 2. So as long as our VD here stays under 2, we're good. Over 2, I mean, we're good. Okay, so that's basically the circuit. It looks more complicated than it actually is. And so now, do we have time? Or are we out of time yet? Yeah, we're out of time. Okay, so let's start our quiz. Let's see, what do we have here? This is our quiz questions.